Welcome or welcome back. In this segment, I'm going to show how you can run auto-indexing programs using CMPR. Now I should mention to start out with that CMPR or CMPR is providing an interface to 3 auto-indexing programs, but these programs are not actually, they're not written by me for one thing. These are programs that have been in existence for quite a while and are written by a number of different authors. The programs available are ITO, which was written by Jan Visser quite a while ago. It's still one of these trusted and true programs that are used by and quite useful. The DICVOL program was written by Ali, I'm not sure how to pronounce this, Bultif, and Daniel Louer, and they have continued to improve it. The original program that was distributed in CMPR was the 1991 version of DICVOL. It's been updated significantly in 2004 and now 2006, and the DICVOL06 program is known in CMPR. And then there's the N-TREOR program, which was then updated and called N-TREOR. I don't have the reference here for the latest version of N-TREOR. The group from Bari, from Carmelo Giacovazzo's group, and I think Angela Altomaria is the first author on that paper. Sorry they don't have the paper listed here. And these 3 programs use different approaches to how they do indexing. And in many cases, one of these programs may succeed where the other ones don't. I'll run through an example here where they all work quite well. But there are good reasons for running one program versus another. Now, let's just talk generally about how one uses auto-indexing. Of course, the concept here is that we have a powder diffraction pattern. We're looking for a unit cell that matches these. The first step in this process is that you need to take your raw data and develop a set of peak positions. And there are many different ways that people do this. In my opinion, probably the best thing to do is to scan through the pattern, visually pick out where approximate peak positions are likely to be, and then use a profile fitting program to fit peaks. And you may want to discard some peaks. Any peaks that look, for example, to have different widths than are wider or significantly narrower are questionable. If they're significantly narrower, they may come from another phase. They could even be single crystal peaks coming from a single crystal. So, for example, sometimes on our instrument we will see, working with low temperatures, individual ice crystals forming on the outside of a capillary and from condensation. And these ice crystals, since you're seeing the diffraction from a single grain of ice, can be much sharper than the powder diffraction data. Likewise, peaks that are very broad also could be impurities, or could be more than one peak that's superimposed, more than one reflection that's superimposed, in which case the question, you can potentially confuse the auto-indexing because it's going to be looking for 2 peaks at different positions from the composite, from the overlap of the 2 peaks. Anyway, once you have your list of peak positions, then you want to run the auto-indexing program or programs. Not all cells that these programs provide are good matches for the pattern that you've started from. So you want to compare the reflection positions that are generated with the raw data or the peak positions you've used. If you don't get a good matching cell, in some cases you may not get any cell at all, you want to change the input parameters to the auto-indexing program and then go back and repeat step 2 by running those programs again. If a likely cell is found, Then you want to look for related higher symmetry unit cells, and you want to explore, let's correct this while we're here. Let's take in a comma, and that should say unit cell. So you want to look for higher symmetry unit cells, and you want to explore possible extinction conditions. We'll take a look a little bit at how that's done. Then once you have what you think is a good cell, it's a good idea to check it by doing a labile or poly fit to the pattern and see how well the unit cell really does match the reflection intensities in the pattern. And that's also a good way to start looking a little bit at symmetry. You may think that there's an extinction system present, but when you try to do the labile or poly extraction, you realize that reflections that have been eliminated from the lower symmetry really do matter. So looking at the R factor, you expect when you remove an extinction condition, even if the extinctions are really there, the pattern fit will be slightly better because you'll be able to better fit the noise. But you should see a significant change when you get to a point where you're removing symmetry that's really needed. Okay, so let's get started on actually running CMPR. Okay, previously we loaded in a diffraction pattern. We located peaks and fit them using CMPR. Now we're going to go back and we're going to index those peaks, or at least we're going to run them through in an auto-indexing program and see if we can come up with a cell that matches them. So let's start CMPR, and since the screen resolution is a little small on this display, let's make the CMPR window a little smaller. Let's move the plot over here, and let's read back in the file that we ended up with last time. So it was in My Documents, and it was a CMPR project, and there it is right here. So we read it in, and we get a clue to the fact that something is wrong by the fact that if we look at this, the scale on this is so large. Well, let's take a look at the two data sets. We can actually click first of all on each data set, and we see that the diffraction pattern, not surprisingly since it was fine before, is still fine. But the peaks clearly have a problem. So let's take a look and see what's going on. If we go to Edit File, we can select the peaks. And as we scan down, we see a bunch of peak positions and their intensities. And if we scan over, we can see their widths, the eta values, which is, to remind you, 0 if the peak is Gaussian, 1 if the peak is fully Lorentzian, background value for each peak, and a peak height. And so if we scan down these, we see, okay, we have a peak right here which has 0 intensity. We don't want to index that, so let's change that to 0. That was the peak where we had where we accidentally added 2 peaks. And furthermore, we can see over here 3 peaks with absolutely huge positions, which is of course pushing this way out. And let's get rid of those as well. So let's change that to 0, let's change that to 0, let's change that to 0. Oh gee, there's our pattern. While we're at it, let's get rid of their intensities. Okay, and so now we can see the diffraction heights, and because this pattern has so much background in it, we can see the background shown as the background for each peak. We have our peak intensities in here. We're ready to go to the index where we'll be able to run an auto-indexing program. First step is usually to select a peak list. In this case, since there's only one peak list here, the program has selected it for us. Otherwise, we would have had to pick something from this menu. Okay, and if we look here, we can see the peaks, and right now they're ordered by decreasing intensity. We can also order them by 2 theta, and now we see the 2 theta values that we've set to 0 at the top, and since they're set at 0 and their height is 0, they're marked as do not use. the rest of the peaks are selected to be used. And we also need to set a wavelength for this, which is 1.5406. And we're ready to select which programs we want to run and how we want to run them. So as a start, let's try using all three of the programs. Running the programs allowing for triclinic symmetry slows the programs down quite a bit, so we probably don't want to do that unless we see that we don't have any other choices. One other choice that we can do is that we can select options for the programs. The default options are probably a pretty good place to start, but just to show you an example, if we select DICVOL, we see a list of many parameters that we can go through, and we can change them. So for example, if we wanted the default, as it says down here, the maximum volume for trial unit cells is 0, and if we keep reading down here, if volmax equals 0, the default is 2500. So we could change that, for example. We don't have to, but if we want to consider unit cells up to 3000 cubic angstroms, we just set a value for volmax. Another choice that we have is whether we're going to run the programs in foreground or in background. We'll try it each way just so you can see how that works. And finally, where do we want to run the programs? So I don't think we want to run this in the CMPR directory, so we could either edit it or we could use browse. Let's run them in my documents. And so let's try background first. So we'll select to run the programs in background. This means that we can continue running CMPR while the auto-indexing programs are running. This is something you might want to do if you were running a particularly long program. So we'll say, okay, here's our peak list, everything should be set up. We run the programs, pops up the windows telling us that the program has been started, and then when the indexing programs finish, which was so already, we get a message saying that the programs have finished and telling us that we can use review output in the index tab to load the results. And we would do that by clicking here, picking the file that we want to use, and if we look here, we can see that this is the one, since this is the newer of the two. And again, I happen to like using details, and then I can put modify, sort by date, and I can see this is the file that we just created. And let's go ahead and do that just to see what happens. So we click on that, we open it, and it's warning us that that file contains the peak list. Do we want to overwrite it? And we could say at this stage, no, let's not. And we can provide a new name for the peaks. So now we'll have two peak lists. Okay, so what's just happened? It's loaded for us a browser window which shows us the cells that were located in each of the three programs we ran. And it's opened an output file browser for each of the programs. So here's the output from ITO. That's a little big for us, so let's make this a little bit smaller. Let's do the same thing over here. So this is the output from DICVOL. And then finally, let's move this one up. Here's the output from N-TREOR. And we could go through and take a look at these, and it's probably a very good idea too, but I'll leave that as an exercise for the user. Okay, so what we can do at this stage is we can view some of these cells. So taking a look here, we see that ITO has come up with 4 very similar orthorhombic unit cells, all having about the same unit cell volume, all having very similar lattice parameters. Really doesn't matter which one we look at, so let's choose the last one. And if we look at this, we'll see that it came up with 4 different cells along here, And if we scan down a little further, it's suggesting that it's possibly hexagonal with significantly larger lattice constants. And it's saying that this lattice can index 29 of the 32 lines. At this point, I would have liked to have seen CMPR pick that up and give that as an option, but at this point it's not doing it. So if we want to look at that, we should do it manually. But let's start by looking at the related orthorhombic cell that it came up with, and we can do that by just clicking on, we don't want to restart, clicking on View, and when we do that, it loads the generated positions and the peak positions we started with. Now, since we have the raw data here, it's a lot nicer to look at the pattern that we generate on top of the raw data. So let's pick, we'll look at the raw data, we'll do that again, and now we can see the data as well as lines generated for where the peak positions should be. And if we zoom in, and it will certainly help to make the screen a little larger, we can see quickly that this is indeed drawing a lot of peaks in about the right places. So, but let's zoom in a little further and see what we see. Well, clearly there is no peak here, but that's not really a problem. Maybe it's extinct, maybe it's just weak. But here, this doesn't look very good. We see two peaks, and this is clearly not a K-alpha 1, K-alpha 2 splitting, showing up where we see only one peak at low angle. And using the arrow keys, we can scan along, and we see that, in general, this lattice is doing a pretty good job of indexing the peaks, except for that one right there. We have not indexed that one at all. So, come to the conclusion, here we've got one line where, let's zoom in for a second, where there are clearly two. So, is this a good cell for this pattern? Only if we're going to work on the assumption that there's an impurity present as well. So this is probably not a great indexing, but it's certainly one that ought to be considered, and I might be tempted at this stage to do a Levi fit. Let's take a look at the main CMPR screen, and we'll see where the edit cell has been used to generate the unit cell. And if we wanted to, for example, we could test a space group and see how the extinctions match. Let's zoom out a little bit, and let's try putting in a space group here. Say P21, 21, 21, since that's, and when we do that and switch over to here, we will see that the yellow lines are now extinct. The yellow diffraction lines are no longer present, so we can't rule out P2121, P212121 based on extinctions, at least not at low angle. We'd have to work a little harder at this, but that's certainly something that's of interest. Alright, so now let's try going back to the cell index, and let's take a look at one of these monoclinic cells, and you'll notice that both DICVOL and NT-REOR came up with quite similar monoclinic cells. So let's take a look at the DICVOL output, and it shows us the output that it came up with, and it should have changed to plotting that, and we can double check by going to CMPR, and now we see that it's loaded the monoclinic cell, it's wiped out our space group for us, and let's zoom in and take a look at this. And okay, well, now we have two lines. They're not quite in the right places, but at least we have several lines. We might be interested in seeing what the indices are on these lines. If we press H in the area, we'll see that there are 3 diffraction lines here in this area. There's the 0, 2, 0, the 1 bar 0, 1, and the 0, 1, 1 lines. And those indices will disappear after a little while because if we change the zoom, they will stay where they are. And so far, this seems to be doing a better job of indexing all the lines, including this one here that we didn't index before. So based on this, I would say this is a much more promising lattice to consider. Last thing we might want to do is, since the Ito output suggested a hexagonal cell, let's try that one too. So what do we need to do? We need to go back to the Ito output. So here's the Ito output, and if we scan down in here, let's see, where was that? Okay, so the lattice constants are A, and of course B equals 15, and C equals 5.8. So let's see, can we, this is always a little tricky on such a small screen, see if we can bring everything so we can see it. So let's select hexagonal, okay, 15.35 and 5.38, and all the other information is the same. We'll select the data set and we'll ask it to recompute based on these values. Oops, and it changed. Okay, will it recompute for us? No, it doesn't seem to want to recompute. I'm not sure why. Let's see, maybe we just need to start a new one. So let's start a new one. Hexagonal, 15.35. That was 15.35 and 5.38 and compute, and it's created a new peak list called dgen1. Let's also add the data set to the plot, and we can take a look if we go to the plot to see how that does. And you can see already that it's not doing any better of a job of indexing this peak. So this is a higher symmetry cell, probably fairly closely related to this cell here, and but it doesn't. It's no more promising than the initial orthorhombic cell that came up with. So, well, at this stage we have 2 candidate cells that the auto-indexing has found for us. One, I think the monoclinic is a bit more promising, but both should be considered, and probably the next step to do with that would be, for example, to see how well one can fit the peak intensities using a Labai or a polyfit. So if we close this overview window, this index, the cell summary, it will close all of the output files, and we can go back. I just want to show you what happens in indexing if we run in foreground. So let's choose the first set of peaks. Let's run this in foreground this time. All the other input is going to be the same. The DICVOL value that we set before is still there, not that I really care, but we'll run it in foreground. So this time we'll click, again, run the programs, and we'll see that it's running the programs. Ito went by so fast we didn't see it, at least I didn't see it. It tells us that the program's finished, it tells us where it put the output, and if we click continue, it will automatically load that the equivalent of that index sum file for us and put up the output files. And this output is exactly the same as what we did before, so there's no reason to repeat what we did before. But you've now seen the difference between running. With foreground versus running in the background. So that pretty much completes this demonstration.